We're going to talk about a theorem involving limits called the Squeeze Theorem that's going to be useful for addressing some limit behavior. So let me first bring up some graphs from Desmos. So here's our buddy, the graph of sine of pi over x, right? And we remember that we zoom in and it just gets so densely packed in there, oscillating between -1 and 1 infinitely often on either side of 0, that there's no limit here as x approaches 0. But if we look at this, which is the function x times sine of pi over x, and we zoom in, boy, it seems like that function, the limit there should be 0, even though g of 0, right, if we ask Desmos what's g of 0, it says undefined because we've got division by 0 going on. Similarly, if we look at h of x, which is x squared times sine of pi over x, that seems to be approaching 0 as well. But why? What can we say about that? So this is where the Squeeze Theorem comes in. So the Squeeze Theorem is a theorem that says if we have three functions, f, g, and big G, and we know that g of x is less equal to f of x, which is less equal to big G of x, for all x near some real number a, except possibly at a, right? If you look at the last line here, this is all about limits as x approaches a. So remember, we don't care about the values of the function at x equal to a, perhaps undefined. If we know that g of x, little g of x approaches L, and big G of x approaches L, so that's saying that this piece is approaching L, and this piece is approaching L. Well, what can f of x do? This is squeezing or pinching down towards L and is smaller, so it's pushing f of x up. This is bigger than f of x, but it's somehow creeping down towards L. So that tells us that f of x must approach L as well. Now, the tricky thing with the Squeeze Theorem is figuring out what these functions, little g and big G, are going to be. In this class, you're going to be really guided towards what those functions should be and not expected to figure them out for yourself. If you go on with math, you may encounter some opportunities to have to figure them out for yourself. Let's go back to these graphs. Let's take a look at g of x, which is x times sine of pi over x. Wow. This blue graph is always less equal to something that looks like that. Boy, that looks like absolute value of x. Huh. And always greater than or equal to, that looks like what happens if you flip absolute value of x upside down. Huh. Okay, let's go back. That is actually the trick to a limit there. I'm not going to go through the details because the algebra with the absolute value gets a little messy. Let's take a look at this. X squared sine of pi over x. Let me plot x squared. Oh, and let me plot minus x squared. Aha. Yeah, and that would make sense because sine of pi over x, oh, we know something about sine of pi over x, right? Let's come over here. So we know that -1 is less equal to sine of pi over x is less equal to 1 for x not equal to 0, because this is not defined if x equals 0. So if we multiply that by x squared, and x squared is always greater than or equal to 0, so if we multiply every piece of this inequality by something that's greater than or equal to 0, then we get this new inequality. But now let's think about this. The limit as x approaches 0 of minus x squared, this is a polynomial. This is a continuous function. So therefore the limit must be equal to the value of the function. Well, the value of minus x squared when x equals 0 is just 0. Also, the limit as x approaches 0 of plus x squared, just another polynomial, that's 0. So now we've got a limit for this function. This is the one that I was calling g of x earlier. I've got a limit for this function. This is the one I was calling big G of x. And so the squeeze theorem tells us that since little f of x, so since x squared sine of pi over x is squeezed between minus x squared and x squared, both of which approach 0 as x approaches 0, the limit as x approaches 0 of x squared sine of pi over x is really 0 by the squeeze theorem. Okay? So if we can find two functions, one smaller than or equal to and one bigger than or equal to, and they have the same limit, then we can say that that squeezed function, that in-between function, has the same limit as well. Let's take a quick look at something like this. Suppose that we had some function f of x, and we knew that these inequalities were true. Well, the squeeze theorem says, let's take a look at this limit. Again, polynomial continuous function, so we can just evaluate that function on the right, x cubed, another polynomial, continuous function, so we can evaluate. So since those two limits are equal, then we know that the limit as x approaches 1 of f of x is 1 as well. Notice we don't know anything else about f of x. F of x may be completely crazy, have all sorts of strange things going on. As long as it satisfies these inequalities, though, we know that its limit must be 1 because the limits of these two outside pieces are 1 as well. In class, what we're going to do is we're going to take a look at how can we use the squeeze theorem to get at the question of what's going on with, so our big question is going to be the limit as x approaches 0 of sine of x over x. Notice my numerator, sine of 0, 0. My denominator, x approaches 0, that approaches 0. So this function is not defined at x equals 0. So it's not continuous there, so we can't just, substitute in x equals 0. It's a little bit subtle to figure out what we should squeeze this with. You're going to do an activity that will walk you through it. What I'm going to ask you to do in the questions on the guided practice is to look at some graphs and start building up a foundation for that.